My name is Gil Goviazin, and today I'm going to present my PhD thesis about the mechanical, thermomechanical, and metallurgical comparison between WAAM and bulk 316L stainless steel material. This PhD thesis was supervised by Professor Daniel Rittel and Dr. Amnon Shirizli at the Technion. So what WAAM is? WAAM stands for wire and arc additive manufacturing. This specific method of additive manufacturing is it uses regular welding machine and regular welding wires, and by maneuvering the melt pool, we can construct our final geometry in a layer by layer fashion. So finally, we'll have our final geometry, but the surface of such geometries is pretty much rough. Hence, this specific method of additive manufacturing is best for large parts. How large those parts should be? So here is an example of such large parts. So this bridge in Amsterdam, you can see its dimensions up here, is huge and was printed in one piece. This dome of a high-pressure vessel that was sent to space, you can see its dimensions in inches here. And who knows, maybe one day we'll all go to Mars and build our homes in this way. So we started with the work of Shirizli and Gleb in 2019, who did plastic deformation on additive manufacturing material by flow forming for the first time. What they did was to print a thick-walled cylinder by using 316L stainless steel. And they used this thick-walled cylinder and they flow formed it, meaning that they did massive plastic deformation, and at the end they got very thin-walled long tube. But this tube had a very high ultimate tensile stress of almost 1.4 gigapascals from this specific material. However, after their study, many questions were left open, like what will happen under different loading conditions and different loading directions? What is the reason for such high UTS point? The residual stresses of this material are enormous, and it's not a workable piece. How can we reduce those residual stresses? What about the anisotropy of this material? And what about the Taylor-Quinney coefficient, which is the thermomechanical coupling of this material? And of course, how it will behave compared to a bulk material. So before we jump in all those things, please take a look here. What you can see here is a process named flow forming, which they did. In this specific process, it's like pottering. When we push our hands against the clay and then we pull them and we construct our final geometry, but instead of our hands, we use wheels that press against our material, and the material starts to flow in the other direction. You can see here the yellow line. This yellow line represents the starting point of this tube that is this height already. It started here and it is here already. So it is a very massive plastic deformation process. Our specific study started by printing thick-walled cylinders, and we machined out of them specimens for compression, specimens for tension, and specimens for combined shear with compression and shear with tension. Those specific two specimens are analyzed using a hybrid method of experimental and numerical methods. The most interesting result that we got after doing static and dynamic testing, the dynamic testing were done by split Hopkinson bar, was those results here, which were also compared to bulk material. The red lines represent the WAAM material. And the interesting point here is that concave upward behavior of this strain hardening, which is completely different from a bulk material in blue here, which does not have this concave upward hardening behavior, which was very interesting for us and led us to our first publication, which is down here. So after we saw those results and we saw that we also got a very high UTS point, we decided to start with the same process of taking a thick-walled cylinder and flow forming it into a thin-walled tube, but we wanted to make it a much workable piece. So what we did is that we sliced it into rings, and we took those rings to different heat treatments. The idea was to reduce the residual stresses to minimum while remaining these high UTS points. Each set of rings then was tested using a ring hoop tension test, as you can see it here, and it was sliced open and the deflection was measured. This deflection measurement led us to the calculation of the residual stresses of the material. So if we'll take a look on those results up here, what we have here is the UTS point, the ultimate tensile stress, against the heat treatment temperature. We can see that after the flow forming process, but before heat treatment, we already got the same high UTS point of 1.4 gigapascals. But then we started doing our heat treatments. And what we saw is that there was a little bit strengthening of the bulk material at 400 C, but much more strengthening of the WAAM material at 600 C. The reason for this initial very high ultimate tensile strength, and later on too, were nanotwins, which were much denser in the WAAM material than in the bulk material. So now we know the reasons for this high UTS point, but what about the residual stresses? So as we increased the heat treatment, the deflection decreased, which is pretty much was obvious. But what was interesting here is that bulk material did not reduce its residual stresses at its maximum UTS point, while the bulk material reduces very much its initial residual stresses to a very negligible level after this heat treatment, while remaining this very high UTS point. However, one point is still left open. What is the reason for this increase in strength of about 200 megapascals here? So to answer this question, first we have to see that there was no phase transition in those heat treatments between node heat treatment and the 600C heat treatments. There was no phase transition. And why is that important? Because using massive plastic deformation combined with no phase transition and accompanied with moderate heat treatment temperatures leads to a phenomenon known as anneal hardening. So overall, we were able to achieve a 300 stainless steel material with 1.6 gigapascals UTS. It is almost 3 times more than the spec one. Those results were published here. Going on to our thermomechanical study, we can take this example of a nail that we hit it on the head. And when we touch the nail's head, it feels warm because under dynamic loading, adiabatic conditions are deemed to prevail. So we decided to study this thermomechanical coupling by the commonly used integral Taylor-Quinney coefficient, also known as TQC or beta int, which in general is kind of efficiency value because we take an output and we divide it by the input. In our specific case, the generated heat by the plastic work. So the plastic work itself can be calculated from the data that we have from our Fleet-Hopkinson bar, because it's the integral of sigma d epsilon. The density and heat capacity of the material can be measured, but how can we measure the temperature rise? So Taylor and Quinney, what they did was to deform rapidly a specimen, and then the specimen fell into a calorimeter. So the output was already the heat. However, today, most scientists use infrared detectors or infrared high-speed cameras. However, the correlation between those two methods was never tested. So we decided to test it. Testing the correlation between those two methods led us to the conclusion that they are identical and it can be used. This specific result was on the cover of Experimental Mechanics journal. Going on to study our specific material for its Taylor-Quinney coefficient, we took the same thick-walled cylinder and we machined out of it specimens in all 3 principal directions, theta, r, and z. And what we got was that we saw an anisotropy in the mechanical properties of the material. which can be seen even better here. We saw that the specimens in the theta and r directions were very anisotropic, and they started with a circular cross-section, but ended up with ellipse-like cross-section, which is very anisotropic. However, the z direction ended up with the same circle cross-section, so the z direction was kind of isotropic. Using this data, we decided to calculate the TQC value, this thermomechanical coupling. But what we got was a very large scattering in the values that we saw. We sometimes saw values of almost 0.7, and sometimes we saw values of about 0.15. How can we explain it? So we thought that the reason lies in the fact that we used an average stress-strain relation, which means that we use the regular relation measured by the strain gauges of the split Hopkinson bar, which gives us an average stress-strain relation over this specimen. But this was exactly the same way it was done in previous studies. And previous studies concluded that in anisotropic materials, the TQC will also be anisotropic. But is it? So to answer this question, we decided to use an infrared high-speed camera and not a detector, because the camera has a much better spatial resolution. And why is that important? Because when we take a look on anisotropic material, when we take a look at isotropic material, the heat temperature map is pretty much homogeneous. So you can see that it doesn't matter which pixel will I take from here, I will get pretty much the same heat all over this specimen. However, when we take anisotropic materials, the heat temperature map is very heterogeneous and not homogeneous. So it's very important which exact pixel do we take. And this is why the spatial resolution of the camera is much better, because if we take here, let's say the same average stress-strain correlation, so this one will be constant. If we take the minor diameter temperature, which was about 36 degrees, we get very low beta. But if we take this one, which was almost 110 Celsius, we get a very high beta. So this explains our scattering. So what we thought that we should do, because here the deformation here on the major diameter is much larger than on the minor diameter, we decided to use a local instead of average stress-strain relation. But how can we get this local stress-strain relation rather than the average stress-strain relation when we use split Hopkinson bar? We did it by using finite element analysis. We calculated Hill's plasticity model by the experimental data that we got before that. And to validate our calibration, we were able to reproduce the measured signals of the split Hopkinson bar and the average stress-strain relation. And we were able to reproduce a very nice fit to the deformation pattern of the specimen. Now we could take those specific elements and compare them to the heat that we measured on the major diameter, and those elements and compare them to the one we measured on the minor diameter. So taking this local approach rather than average approach led us to see that in general, it doesn't matter which direction we measure, we finally got pretty much the same Taylor-Quinney coefficient in all directions. So to be sure that this result was right and true, we did it in the other way too. We took this value and we put it back into the simulation, and we were able to reproduce the same heat map as the one that was measured. So what I'm trying to say here is that we were able to present that the TQC is isotropic, even if the material is anisotropic. Thus, we were able to contradict previous studies. So if I will, this study was published in this journal. So if I will conclude and summarize everything right now, we started with the basic mechanical properties in different directions and different loading conditions of this specific material to see its basic mechanical properties. Then when we saw this concave upward behavior, we continued, and we were able to activate nanotwins using large plastic deformation process. And then we were able to activate the anneal hardening phenomena to achieve a 316L material that was able to that was reached the 1.6 gigapascal UTS point. Before we continued with the thermomechanical coupling, we were able to see that infrared camera and detectors have the same results. And finally, we were able to present and show that the TQC value of is isotropic regardless of mechanical anisotropy. Thank you very much for listening, and I'll be glad to answer any questions.